Hi folks, we are on Unit 4, Day 9, and we're going to talk about derivatives of some other types of functions that we can't do using the derivative rules from the previous day. So in Day 8, we talked about derivative rules that were based on exponents of x, so the power rule, the sum and difference rule, and the constant multiple rule. And we could take the derivative of a lot of functions using those rules, but not all functions. So today we're going to look at exponential and logarithmic functions, and then in the next day's note we're going to look at derivatives of trig functions, which don't kind of fit into those other categories. So first, to kind of think about what the derivatives of these different functions might look like, I want to think about what the derivative is. So remember that the derivative is the rate of change, the instantaneous rate of change of a function at that point. So let's kind of think about what each type of graph that we know might look like. So I'm going to just kind of sketch some functions. So what are the different kinds of functions that we know? Let's start super easy. Back in grade 9, you guys learned linear functions, right? We had the equations of a line. So if this is my f at x, what would the slope of the tangent look like for that? So what would the derivative of that be? The slope of the tangent to a line is always constant. So the derivative might look something like that, just a horizontal constant line. So thinking about what the shape of the derivative would be based on what the equation or what the function is doing and what kind of equation would model that rate of change. So the next kind of functions that you guys learned were quadratic. So if we kind of had, whoa, that's a bad parabola, but we'll go with it. If we have a parabola like that, thinking about what's happening to the rate of change. I'm going to use my ruler as a tangent line here. So here, the rate of change is a big negative, smaller negative, 0 at the vertex, and then small positive, big positive, big positive, big positive, getting bigger. And we know from yesterday that the derivative of a parabola, or the derivative of a quadratic, is actually a linear function. So this parabola has a big negative slope out here and a big positive slope and kind of smaller negative and smaller positive like that. So the derivative, we know that the derivative of something squared would be a linear. So if we have kind of a parabola like that. So I'm just kind of want to think of this as the graphical representation. So if we extended that and had maybe a cubic or any kind of higher degree polynomial function. Let's think about what the graph of the derivative might look like. And again, I'm not using any kind of scale here, but I know if I'm going to pull my ruler in again, the slope of the tangent out here is a big negative number. It's steep going down. And then the slope of the tangent is still negative all the way here, but it's getting smaller and smaller. Now what happens when we have this turning point? The slope of the tangent there is going to be 0. So I know that I would have a slope of 0 there, and that this is in the negative side, going bigger and bigger negative. Now here, between this turning point and the next, the slope is positive. It's kind of getting bigger positive and then getting smaller positive as we go kind of up to there. And that second turning point would also have a slope of 0. So I'm going to put a 0 on my derivative. And then it's negative getting bigger and bigger and bigger and keeps getting steeper negative. So this was really big negative getting to smaller negative. So really big negative getting to smaller negative. And then it goes positive, bigger positive, and then smaller positive. And now it goes into the negatives. The slope over here would be negative of the tangent. And it gets bigger and bigger and bigger negative. And look at that. We end up with a parabola, which we know that the derivative of something cubed would be something squared. So you'd have a square x squared term in your derivative of a cubic function. Okay, so other kinds, and we can kind of go into higher degree polynomials there too. What about other types of functions that you guys have seen? So you guys have seen like a square root function. And we talked about the derivative of this when we did the first principles in, I think, day 6. So here, looking at the slope, here it would be very big positive in close to that 0. Very big positive slope. And the slope here is always positive, but it's getting smaller and smaller and getting closer to 0, but it's always positive. So the derivative of this function would be really big positive, getting down to smaller positive, but never going into the negative. So it's got an asymptote there. Some interesting ones. What else can we look at? We maybe can take a little bit of a look at a rational function. So if we maybe had like a graph of 1 over x, and I believe you guys found the derivative of that yesterday. So here, what can we see about what the slope of the tangent is doing? So here, the slope of the tangent is small negative, going towards bigger, 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 bigger negative. And then there's an asymptote, so there's no derivative there. And then it's big negative going towards smaller negative. So this never has a positive slope. So the derivative would actually kind of mirror this shape here and be down in that side there. So that's what that derivative might look like. Another type of function that you guys for sure know is if we wanted to look at a trig function, and this is going to come more into play in tomorrow's lesson, but let's just take a little look. So here, okay, there's a graph of sine x. Now let's think about what we would know. So this derivative starts positive, gets smaller and smaller positive until it's at 0 there. So where it's flat, it would have a derivative of 0. Then it's going down, down, down. This is all negative, bigger negative, smaller negative, 0. So where I have that turning point, I'm going to put a 0 for my derivative. And then it's positive, kind of getting bigger. So it's going to kind of go like that. And then this was small negatives going towards bigger negatives and then back towards smaller negatives. And this was bigger positives getting smaller and smaller positives. So that probably gives you a little bit of a clue what we're going to see for the derivative of sine x in the next day's note. But what I really, so this is kind of how we see what the shapes of the derivatives would look like. Now let's look at our exponential functions, since it's right in the title, right? Yeah. So if we have an exponential function, and that's not a great graph of one, but we may have some kind of scale. Think about what's happening to the derivative here. Here the derivative is positive, but it's very small. So it's small values. And then it's continuing to get bigger and bigger and bigger and bigger. So it starts out small and It increases and it always stays positive. So that kind of looks like the graph of an exponential function itself, right? If we kind of thought about what the derivative might be doing, it looks kind of similar to the actual function. And it's not exactly the same normally, except for one particular special case. And that's what we're going to look at in the next part. So there is actually one special function where f at x actually equals f prime at x. And it's a special example of an exponential function. Okay? And there's a lot of other really important things about that function as well. I won't get into too much of it, but I will link a bunch of videos. So these videos will be linked in the outline if you want to kind of take a look. There is this special number. It's an irrational number like pi, and it's called e. And that is the function where e, if f at x equals e to the x, so it's an exponential function, then f prime at x equals also e to the x. So that's the one special function where the graph of the function and the graph of the derivative are exactly the same. All exponential functions are going to be similar to their derivatives, but they'll be multiplied by a scale factor. So this is that special number, and it has its own, it's equal to its own derivative. So the function where the value of the function is equal to the value of the derivative at every point is the kind of basic exponential function, but with a base of e. So that's the first thing kind of that you guys probably would have seen with this e, or Euler's number, that it comes up because it is really important, because it helps us find derivatives of exponential functions, because it has that very unique special property where the function itself is equal to its own derivative. So e, again, is an irrational number. It keeps going. You don't have to memorize it. It's about 2.7. That's good enough. There is an E button on your calculator almost for sure. Neat things about E, which you don't have to memorize or really kind of know at all. So this is kind of an interesting identity. If you've done data management, you would have looked at factorials, and factorials just mean that I'm just going to kind of unpack this notation a little bit. So say, for example, 4 factorial, that exclamation mark, it looks very exciting, but it just means kind of multiplying all of the numbers from 4 on down. Okay, so 5 factorial would be 5 times 4 times 3 times 2 times 1. It's just a notation to say I'm multiplying up all of those numbers. And this kind of weird notation, it's called sigma notation, and it means I'm going to add up a bunch of terms. So this is a way of writing an infinite series, that we are going to add up an infinite number of terms. So if we start and say 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial for forever, going to infinity, this value actually evaluates out to this irrational number e. So that's pretty cool. In grade 11U, you guys may have taken a look at compound interest and compounding periods. So remember, if the interest is compounded more often, that you will end up getting more money. And there's something called infinite compounding. So I'm not going to go through all of these, but you can kind of figure out if you invested, say, at 1%, or I guess this would be at 100%, or if you kind of increased the compounding periods and divided the interest, and if we kind of did monthly and continued on, so investing $1, so kind of kept going like this and got more and more frequent compounding, so taking the percent and then maybe dividing by 365, but multiplying that interest, adding that interest on that many times. If we kind of kept going here and you end up actually taking like the limit of this, you will get closer and closer, and you can kind of evaluate these values. You get closer and closer to the value of E. So the limit as n approaches infinity, so this ends up being of 1, where 1 plus 1 over n to the exponent n actually equals E. So as n gets bigger and bigger, more frequent compounding, that ends up having an application to finance. Area under the curve. A pretty cool thing happens here with the area under the curve of f at x equals 1 over x. So finding these areas is really the second big idea in calculus that we don't cover this year, but you guys, if you take calculus next year, you'll see it. In this function, if you want to find an area that's exactly equal to 1, it ends at E. Let's see. Lots of weird things. Here's this weird function, f at x equals x root x, the x the root of x. Finding the maximum of where that function happens is at E. So I'll link these videos, just some kind of interesting things about Euler's number, or this very special irrational number. But what the most important thing for our purposes right now is that this function has itself as the derivative. So it's actually the easiest derivative rule ever. And you might be thinking like, all right, well, what can I even do with that? I mean, how many marks am I going to get on the test for saying, oh, with this one, the derivative is just equal to itself? Like 1 mark on the test for that, not very much. But we may also have something where the exponent in that exponential function isn't just an x. So you might have e to some other function, so e to another exponent like e to the exponent x squared perhaps. So then the derivative rule is a little bit more complicated. It's the original function times the derivative of the exponent. So we're going to combine that together with the same rules that we did yesterday. So here we've got y equals e to the exponent 3x squared. So the derivative dy dx is the same function. So I'm going to keep it exactly the same. E to the exponent 3x squared times the derivative of the exponent. So now I'm going to take the derivative of 3x squared, which is 6x. Sometimes this kind of gets lost, so I'm just going to rewrite things in a little bit cleaner order. Put that 6x and then e to the exponent 3x squared, just so that it's very clear that that's the exponent and that's a coefficient. The next one, f at x equals e to the exponent negative 3x over 9. So this is kind of like, I'm going to think of this as 1/9 times e to the exponent negative 3x. That's what I'm really thinking of this as, with that 9 on the denominator as a coefficient of 1/9. So when I find the derivative I keep that 1/9 there because this is a constant multiple. I keep e to the negative 3x the same. And then I multiply the derivative by the derivative of the exponent. So what's the derivative of negative 3x? It's just negative 3. So then you would simplify. I've got 1/9 and a negative 3. So it's negative 1/3 e to the negative 3x. And we're going to continue with the derivative of logarithmic functions in the next video.